Okay, getting next into some analysis tools, the evolution of analysis tools. People have obviously been trying to get their arms around moisture migration in materials for a long time. One of the earliest things people did are try to do manual mechanisms, manual analysis tools like the dew point method, where you just essentially use the thermal resistances across the wall to draw the temperature drop, and you figure out the dew point, and you figure out where in that wall the dew point sits, and then that's where you have condensation. Very limited analysis method, not much power there. Now we have more sophisticated computer simulation and modeling tools that do both 1- and 2-dimensional steady-state models. Steady-state model is something that is just a snapshot in time. Or transient models. Transient models are models that actually model cyclical behavior of phenomena that vary over time, like weather. The manual design tools have substantial limitations. For example, the dew point method is really restricted to prevention of sustained surface condensation. Right? If you determine the dew point somewhere, that's really all you can do with it. It's a reasonably crude approach because it's also just applicable to a one-dimensionally layered system. Right? When you do a dew point method, you're essentially applying it to an infinitely long, infinitely high wall under one condition once in its life. So the other problem is that it assumes linear temperature and moisture distribution. And go ahead.
Would you say it's better than nothing, or?
Oh no, it is better than nothing, because all these crude analysis tools, their virtue is that you can use them to check up on the fancy analysis tools where you're wondering, is this right? And that's the point that Eric made, right? You still need a sophisticated programmer to get there. So when I was in graduate school, and I was in structural engineering graduate school, whenever we did computer programming, my professor would say, if you can't get it to 25% of the output of the program on a napkin, you shouldn't be doing this. And that's why there's still a virtue to these things. Therm is a great tool, very sophisticated analysis tool for heat transfer by steady-state analysis. This was developed at the Lawrence Berkeley lab. Uses finite element methods to calculate heat transfer across complex geometries, right? And this is, Walter, this is where you can take a look at that window frame geometry very, very carefully, and you can really drill down and move stuff around and determine the temperature distribution there to figure out, when and where it's going to condense. It's a steady state analysis, right? Just one condition, one snapshot in time, and it also, this particular model does not account for thermal or moisture storage, right? Can't do that. And it does not account for rain, radiation, and changing weather conditions, right? If it's sunny out, if it's overcast out, you have to use other models and sort of crunch them together to make that work. And that's where Eric said, sometime somebody's going to come out with the overarching do-it-all software. It's just not there yet. Transient moisture migration calculations, that's sort of the next step. There you're crunching a tremendous amount of data because you have to deal with all the various material properties, the different moisture transport mechanisms, different weather conditions, different interior conditions, and that can really only be done using computer analysis. And here are the various things that these take into account: moisture storage, weather conditions, and heat flow across the various building envelope materials. And the industry standard for that is a program called WUFI. And because I'm German, I can pronounce it: Wärme und Feuchte instationär, which just means warm and moist in situ. It's been used for 10 years, and they do something that's pretty cool. They validate these calculations through experiment to again give you a bit more data to make sure that you're reasonably in the ballpark. And the American version has been around for 10 years, developed in collaboration with Oak Ridge. Here is just some of the climate data that goes into it. This was from one of my jobs in Baltimore. It just shows temperature curve over a year and then a relative humidity curve over a year. This is part of the weather data that you can put in there that's based, again, similar to Eric's modeling tools, on historical weather data that is contained in the weather file for this program. And this is what the output looks like. First, pretty bewildering. Keep in mind this is one-dimensional. On the left is the exterior of the wall. On the right is the interior, and you're sort of walking through the different sandwich components of the wall. And what it shows you is the temperature within the wall, which is essentially, if you look at the dark red line, that is the instantaneous temperature. And if you actually run the model, it sort of wobbles up and down, and it sweeps across that envelope, which is that red funnel, which is the envelope of the temperature over the year. And then the humidity in the material, again, the dark line is the instantaneous humidity, and the darker colored area is the envelope here. And what we're looking for humidity is that it stays reasonably low, hopefully below 80%. And that is sort of a rough indicator. At 80% in some materials, you start having condensation and you become worried. And it also has a water content of the material that's derived from the humidity at the bottom. And again, it has a sweep and an instantaneous line.
When do you start being concerned about that water content?
It depends on what material you're in and whereabouts in the wall you are, right? In general, that 80 is pretty worrisome, right? Particularly if you have materials that are moisture sensitive. Anything that you shouldn't be putting in the wall anyway. Anything organic, right? Paper facers, that sort of stuff. But in a historic building, you might be dealt materials that you just have to accommodate, and then you have to sort of make your peace with that humidity. But generally, anything under 80, you can be reasonably comfortable with. Go ahead.
Is the water content measurement driven by the material's ability to hold water then? Is that?
Yes, the water content is really derived on the humidity, and it's a type of material and sort of its absorptive capability. So if you have something in here, and I don't know what we got that's completely non-absorptive, right?
Yeah.
The water content will be like near zero. And if it's a porous material, it'll be a bit higher. I generally look at the relative humidity and then also the water content, but the point that Carl made also, this is all kind of voodoo, right? Because the things that you're looking at is you want to look at different cases and different materials and look at trends as you do certain things, right? None of this is absolute, and none of this, unless it's way off the chart, is an actual predictor of performance. You're looking at relative performance.